Hello and good day to all of you. So in this lecture, we are going to learn about the Sun, its composition, rotation, atmosphere, and internal structure. So in the previous lecture, we have been looking at the stars and we had looked at the star types and everything. So so the nearest star, which is the Sun. So now we'll look at more into detail about the Sun and its internal features. So prior to start the lecture, so we have these two learning outcome of this lecture. So the first learning outcome is to understand the sun and why it is belongs to G2 type star. And the second objective is also to learn and understand its rotation and looking at its atmosphere and also the internal structure of the sun. So these two main objectives will be achieved during this lecture. So let's look at the sun. So if you we have many graphical display of the sun, so this is one of them. And if you look at the real or the structure or the inside the features of the sun, so it appears to be like this without the outer atmosphere. So sun is actually only the star of our solar system, and it is the heaviest among the solar system. So all the planets like Jupiter, Saturn, Uranus, Neptune, every planet is smaller than this one. Even we combine all the masses of the planets, it's still not bigger than the sun. So it is a ball of hot burning gases, and it is also the nearest star to the earth. And the light from the sun takes approximately 8 minutes to reach to the earth's surface, and also it is the source of energy for life on the earth. If there is no source of energy, then the temperature of the earth will be increasing a lot. So because of the sun, we have maintained temperature on the surface of the earth, and which is only the survival of the human life. And there about 3/4 of the sun masses consist of hydrogen, while the rest is mostly helium. So these are the composition of the sun. So looking at more on the feature of the sun. So on the sun surface, there are some dark patches which are known as sunspot. So over here you can see this is in a different color display. So I'll show you another display which shows the sunspot. So now you can consider in this figure is these spots are actually the sunspots. So these are patches of the gases that looks darker since they are cooler than the other surrounding surface. So let's looking at the further more about the sun. So one of the more than 100 billion stars are in our galaxy, as we learned in the previous topics as well. So the dimension or the diameter of the sun is 1.3 million kilometers, and the mass is 1.989 e raised power 30 kilogram. And if you look at the temperature of the sun is actually 5,800 Kelvin, which is the surface temperature. And obviously the temperature of the core is much more higher than the surface. So it's about 50 million Kelvin is the core temperature. So it's also contain more than 98% of the total mass of the solar system. So Jupiter contain most of the rest. So if you look at the mass, so this is the 99.8% of the total solar system mass is contained by sun. So as in the previous lecture, we also have looked at the spectral or the stellar classification. So actually there are some classification of the stars. so which are O, B, A, F, G, K, and M. So O stars are the hottest star and M are the coldest stars. So it depends on based on the temperature. So O is the hottest, M is the coolest star, and OB, which is O and B, is the brighter. Stars are rare but very bright. Obviously, the temperature is very high, but these are very huge in size as well with respect to temperature and also the size. So, but they are very rare, but they are much more brighter. If you look at the sky in the night, so you will hardly look these stars in the sky. Maybe the much more brighter stars you're looking at, it will be O and B. And focusing on M is their numerous star, but these are dim star. So if you look at the sun, it actually belongs to the G-type star. So that's why it has the moderate temperature rather than the other stars. So as I mentioned, the surface temperature of the sun is 5,800 Kelvin. So if you convert it to the Celsius, so it's 5,526 Celsius. So what are the actually sunspots? So in this figure, you can see these black dots are actually the sunspots. So the temperature of these sunspots is 3,800 Kelvin, or if you look at the Celsius, so it's 3,526 degrees Celsius. So these looks darker. Why? Because there is a huge difference in temperature. 5,800 and 3,800. So it's 2,000 Kelvin difference in temperature. So sometimes these are quite huge. Sometimes it's 50,000 kilometer in diameter, and which is caused by a very complicated process, and it's not very well known understood by the astronomer. So most probably it can be, predicted by the interaction of the sun magnetic field in internal magnetic field. So now we look at why the sun is considered as a G2 type star. So as you look at in G, we have multiple categories: G05, G1, G2V, G3, and up to so on. So a star which has about zero point 0.8 to 1.15 solar masses, and the surface temperature is between 5,300 to 6,000 Kelvin. So G type main sequence star is converting the element of hydrogen to helium into its course by the mean of nuclear fusion. So this is also the phenomena which is considered by the sun. And G-type main sequence star, which mostly the spectral type, G5, and often called is yellow dwarf or the G dwarf stars, is also the main sequence star, which is luminosity class of V5. So now when we look at here, so all the principle which follows by the sun is passing to this type of, so the spectral type is G2V and the mass is 1.07 and the surface gravity is 4.35 and the effective temperature of the surface of the sun is 5,800 Kelvin and the color index is 0.625. So when it passes through these all processes, then we have defined the sun is G2 type star. So now we'll be looking at the composition and rotation of the sun. So over here, we're just focusing on here. So the composition, as we have already looked at before, so about 71% of the composition of the sun is hydrogen, and 27% is helium, and 1.5% are metals or by masses. So these changes slowly as hydrogen convert into helium in its core, and the outer layer exhibit different rotation, or it's called the odd behavior, when the different part of the rotation of the object move in different angular velocity at a different latitude or the depth of the depth body of the sun. So here is an example or the figure which explain the rotation of the sun. So let's look at the equator first. So at equator, if you focus here, this equator actually takes about 25.4 days to get to this point again. So it means one rotation is 25.4 days, and the pools is at the pool the rotation is different, so it's 36 days over here. So in between it can be explained. So over here is 25 days, then 26, 28, 31, 36, up to 36. So the differential rotation extends considerably down into the interior of the sun, but the core of the sun rotates as a solid body. So the sun core is approximately 25% of its radius are extreme, and the temperature is 15.6 million Kelvin, as I mentioned in the previous slide, and the pressure is 2,250 billion Sat. And the center of the sun density is more than 150 times of the water. Now looking at the structure of the internal structure of the sun and also looking at the nuclear fusion. So initially, similarly like the Earth, we also have the internal structure of the sun. So inside we have the core here. So core is the innermost part of the sun, which is 20 to 25% mass of the whole sun. And radius the radius is 20 to 25%, and where the temperature and the pressure are sufficient for nuclear fusion to occur. And the hydrogen fuses into helium, which cannot itself be fused at this point in the sunlight. So the fusion process releases the energy and the core gradually become enriched in helium. So first internal structure is the core, which is 20 to 25% of the radius. Then the second part is the radioactive zone, so which is this zone we have. So this zone has the convection cannot occur until much nearer to the surface of the sun. So therefore between about 20 to 25% of the radius and the 70% of the radius, there is a radioactive zone in between this radius. So radioactive zone, and in which the energy transform occurs by means of radiation proton rather than the convection. Then we have the tachyline, which is over here. So this point is actually the tachyline. So this is actually the boundary region between the radioactive convection and the convection zone. So this is the radioactive convection above the core, and this is the convection zone. So in between is called the tachyline. Then we have the convection zone, which is over here. So it's actually between about 70% of the sun radius and the point close to the visible surface of the sun. So up to from here, this is 70% up to the surface of the sun. And the sun is cool and diffuse enough for convection to occur, and this becomes the primary mean of outward heat transfer, similar to the weather cell which form in Earth atmosphere. So this was actually the internal structure. So now we'll be looking at the atmosphere of the sun. So there are also different atmosphere. Similarly, we have the Earth atmosphere. So the sun also has the sun atmosphere. So the first of all, we have the first layer in the sun is actually the photosphere. So which is the lowest layer of the sun atmosphere is called the photosphere. So which is over here. And it's about 300 miles or 500 kilometer thick. And this layer is where the sun energy is released as light. Because of the distance from the sun to Earth, the light reaches to our planet is about 8 minutes. So actually the light produced over here. And the second layer of the atmosphere is the chromosphere. So the chromosphere has been divided into two, the lower and upper chromosphere. So this is the smallest region. Small region lies above the color sphere or the photosphere. Then after that, so actually the differentiation of the lower and upper is based on the temperature. So the lower atmosphere or lower chromosphere has 4000 degrees Celsius temperature and the upper is 10,000. Then the last is the corona. So you can see these are the corona effect or the corona atmospheric layer around the sun. So it is highly rare field region above the chromosphere, and this is in millions of kilometers in the space. It can consider sometimes quite big layers. So it is visible during the solar eclipse. So when there's a solar eclipse, so then you only can see the layers around the sun is actually the corona. And the temperature of this corona is around 1 into 10 raised power 6 Kelvin, 1 million degree Celsius as well. So just explaining the another figure which can give you the internal structure and the atmosphere together on the left side. So this is the core of the sun. Then this is the radiation zone in yellow color. The orange is your convection zone. Then if you look at this orange layer around the sun is your photosphere. Then above the photosphere you have chromosphere. Then corona appears to be like this green one. And if you look at the structure of the sun, I mean how many features we have and how you can view. So these are actually the different views. And so at this view you can look at the sunspot, but at this view you can look at the chromosphere. But once you want to have this appearance of the sun, is the corona will be visible quite actively. So with that's all, I think thank you so much, and I hope you have understand about the sun, and hope to see you again.